So today we're starting the Gauss's law unit, right? And the first thing we need to learn about, the first quantity that we need to learn about in order to work with Gauss's law, which remember helps us find the electric field around some non-point charges, but some very symmetric and common charge configurations. So we need to learn about electric flux first, right? And so what you need to do about, what you need to understand is the relationship, like it says on the objectives up here, between the electric field and the electric flux. So you can figure out the flux of an electric field through any surface from a uniform field. The flux of an electric field through a rectangle when the field is perpendicular to the rectangle, and the relationship between flux and lines of force. So hopefully you'll be able to have an idea of how to answer those or do those after today's lecture. So electric flux. So when we're talking about electric flux, right, through a surface, we have to have an electric field and we have a surface, some kind of imaginary surface, a rectangle in space or something like that. And can somebody tell me, does anybody know what the electric flux really is a measurement of? What is the electric flux? No? Anyone hazard a guess?
Wow. It's like how much electric field goes through something. I think I watched a lecture on it, and there was like a hole in a surface, and then that affected how much electric flux is going through.
Yeah, exactly. So it has to do with how many electric field lines or how much electric field is passing through a surface, right? And the surface can be anything. It can be a rectangle, it can be a circle, it can be a sphere, and you could be talking about a closed surface. But any kind of surface that you can imagine, right? We know that there are, if there's an electric field, there are electric field lines, everywhere in space made from the electric field. And the electric flux is just a measurement of how many electric field lines pass through a surface. So it's a measure of the number of electric field lines passing through a surface. So if here's our surface, A would be that, A there is the area of the surface. Let me make sure I write that down. So we're talking about a surface of area, capital A. Okay, so here's a surface, and let's say I have a uniform electric field, right? So we're talking about electric field that's in the same direction and the same strength everywhere. So then we'd have lines coming through. Kind of hard to draw in 3D. This doesn't look very good. But you can imagine we've got lines passing through this surface, right? The electric field is pointing to the right here. It's uniform. And we know that when we draw field lines, the number of field lines we draw is proportional to the electric field. So that should help us figure out a simple equation for this electric flux as a function of the electric field and as a function of the area that it's passing. Right? How would the flux be related to those, the electric field and the area? We can come up with a simple equation.
The electric field times the area?
Yeah, exactly. It's just going to be the electric field times the area, right? The magnitude of the electric field. It's a uniform field, so it's the same value everywhere. And since we're trying to make a measurement of how many field lines are passing through this area, right? Well, if we increase the size of the area, that's going to increase the number of field lines passing through it. And if we increase the strength of the electric field, that's going to increase the number of field lines passing through the surface, right? So the flux, which the Greek letter phi is the symbol that we use for flux, is just the electric field times the area in the very simple situation where there's a uniform field perpendicular to the flat surface. And we're going to expand that and see what happens next if it's not perpendicular and so forth. But that should hopefully make sense to you, right? Why it should be just E times A, right? If we double the area, then you're doubling the number of field lines that are passing through it, right? If you double the electric field, so there's twice as many field lines, you know, in a given region, then you're gonna have twice as many field lines passing through that surface, so twice the electric flux. Questions so far? It still doesn't make sense and probably shouldn't make sense to you why we care about this quantity electric flux. But if you stick with it, once we get to Gauss's law, it should make more sense. It's just think of it as the number of electric field lines that go through a surface. Okay. What if the surface is not perpendicular to the electric field? Let's see what happens next. And for a good, I can't draw this picture that well. So if you take a look in Survey and Jewett on page 721, figure 24.2, that has a better, a better view of this. So in this, what I'm doing here now is I'm going to have the same electric field here, uniform and to the right. Well, I should draw that more uniform, but that's okay. All right, if I've got a uniform electric field to the right, but this time I've kind of tilted the surface. So instead of being straight up down, now it's the plane of the surface is at an angle like this. So E is not quite perpendicular to my area A. This is my area A still, this rectangle here. So what we should be able to see though, is if I draw a similar surface, that's this one here, the one that is perpendicular, the electric field lines. The difference is, well, they both have the same width. Both these rectangles have the same width, what's called W for width. If this is the length of the main rectangle here, this side, then this here is the kind of the perpendicular of the length. I'll label that L perpendicular. That's this side here, right? Compared to this side from the full rectangle. So the number of lines, we can see just by looking, the number of lines that are going to pass through both of these rectangles is going to be the same, right? Because you know, if you're looking from the point of view of the electric field lines, both of these rectangles have the same cross section. So let me write that. But since the number of lines is the same, therefore, also the electric flux is the same. All right, so that means if we take a look at the flux, we can calculate it because we know it's got to be equal to the electric field times this area, the perpendicular rectangle. Right, which is just the electric field times the perpendicular length times the width. And we can tell from the diagram, we can figure out, we can relate this L perpendicular. So we can relate the length from this perpendicular rectangle to the length of this rectangle that we're looking for if we know this angle, right? If we know what we call this theta. If we know this angle theta and we know this length here, we can figure out how this perpendicular length is related to it. Can anybody see the trig function that'll give us that?
Cosine.
Yeah, that's going to be the cosine, right? So from the diagram, we can see that cosine, well, yeah, the length, the perpendicular length is just going to be the length of the main rectangle times cosine. All right, so that means right, if length perpendicular is L cosine theta, that means our flux is going to be the electric field times the width times the length times the cosine of the angle.
So, Mr. Marcus.
Yep.
Does the width of the rectangle or the, I don't know, the material of the rectangle, does that have any effect?
No, well, okay, so the width of the rectangle will have an effect because because it's a function of the area, right? So the bigger the area, the bigger the flux.
No. So that would be the thickness.
Oh, the thickness, no, because it's just a surface, right? So it would be, when we're talking about a surface, we mean a 2D, so perfectly flat. And if we're talking about a uniform, so these surfaces wouldn't really have a thickness.
Okay.
Right. And these are just, so, and you can talk about, you mentioned the material as well. So right now, these are just imaginary surfaces, right? We might make them when we're using Gauss's law, we'll be talking about using, a flat, plane that has some charge on it, will be our surface. Actually, no, that's not true. Usually the surfaces are just going to be imaginary surfaces, right? That we're going to use.
So does that mean that the plane or the rectangle is gonna like reflect what's it called, bend the field and make it point upwards? For example, in this example.
No, well, not these rectangles, no, because these are just imaginary rectangles, right? There's no so we're basically looking at how many surface lines there are, in a given place, in a given region of space, right? So there might, if we put a material there, that might affect the electric field and change the electric field, and that's okay. And then we could still find, what the flux is. But there doesn't have to be any actual material rectangle there, right? If I just imagine a rectangle in space, the flux would be how many lines are passing through that rectangle. So whether there's actually some material there or not doesn't matter for the flux.
Okay. Sure.
So just to finish this equation here, right? And we know that length time width again was the area. So we can say in this case that the flux is going to be the electric field times the area, but this time multiplied by cosine. So if you kind of change the angle of the rectangle with respect to the electric field, right, you change the amount of lines passing through it. You can imagine if I rotated this rectangle all the way, so it just end on in the field, right, this perfectly flat rectangle, then you'd have a cosine of 90 degrees and you get zero flux. And that would make sense because the field lines aren't passing through the rectangle if it's end on. So let's see, we're almost a little bit more with this. We'll go on to the next page here. So a little bit more about this angle theta. So we want to be able to know what that is. So basically theta here theta here can be defined as the angle between E, the electric field, and a vector that's normal to the surface. So like if this is my surface here, right? Do you know what we mean by normal to a surface?
Yes. Perpendicular.
Perpendicular, exactly. Thanks. Yeah, so a vector perpendicular to the surface, right? That can help us give a direction for what, if you think about it, the only way to really specify what direction a surface like a rectangle is facing in space, if you orient it, would be by using this vector that's normal to the surface. So if I draw in, so let's see, again, it's hard to draw in 3D, but this vector would be pointing kind of outwards like this, right? So that it's perpendicular to the surface here. And we would call this our vector A. So if your computer screen is a surface, or is that rectangle, right? The normal to that surface would be pointing directly out of the screen at you, right? If the floor is the imaginary surface, then normal to that surface would be pointing straight up, right? Or straight down, I guess. But if you know, and it's kind of important to wrap your head around this part of it, why we're using a vector that's normal to the surface. If you know that vector, if you know what direction that normal vector is pointing, that's enough to give you the information about which way that surface is oriented. Hopefully, if we do a couple of examples, or when you work a couple of problems, that'll become a little more clear. So we're going to define this vector A. That for any of these Gauss's law or any of these surfaces that we're going to be working with. So the vector A, it's going to have magnitude of the area. So it's got the magnitude of So this vector is going to be longer for the bigger the area of the rectangle. And the direction, of course, is this direction, normal to the surface. And the reason we do that is because now our electric flux, which we said was EA times cosine of this angle, well, we remember from our definition of the dot product that if we take the dot product of two vectors, we get the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. So that's exactly what we have here. We have a magnitude of one vector, the magnitude of another vector, and the cosine of the angle between them. That's how we defined theta before. So that just equals our dot product, E dot A. So this formula for, so this is a little different, right? So when we started, we had a flat surface, electric field, a uniform electric field perpendicular to that surface. We just had the magnitude of the electric field times the area. And now we're seeing, well, if they're not perpendicular, then we need to take the dot product between the direction of the between the electric field vector and the area. So this formula is good. This is for the flux of a uniform field through any flat surface. All right. And you can go back and check the lecture video on the dot product and there's stuff from Survey and Jude on the dot product. It's a quick thing to look back up if you're rusty on dot product. So then finally you want to get the most general form of this equation, because what if the electric field is not uniform, and what if the surface we are picking is not flat? So what if E is not uniform? or if our surface A is not flat. Well, what do you think we're going to do in that situation? What do we usually do in physics when we have when we run into a complication like that?
We add another variable.
Okay, you could add another variable. That's good thinking. Not exactly though. What if instead of one flat rectangle, it was two rectangles kind of pasted together? How would we find?
Oh, I see.
Yeah, you see what I'm getting at?
So then we get the separate area equation for the different shapes, right?
Yeah. So if we had, yeah, exactly. If we had two rectangles pasted together, we would calculate the flux through the first one and the flux through the second one, and then add them up. Right. So what we're going to do in general, if we have you know, a non-uniform field or a non-flat surface, is we break that surface up into lots of small, approximately flat pieces, and we find the flux through each of them and add them up. Right? If you look at any surface, if you kind of look closely, if you kind of zoom in close enough, if you zoom in close enough, any part of it will look flat. So what we're getting to is an integral. So the idea is to break up the area into lots of small, approximately flat pieces. Find the flux through each of those. And then add up. So the way I'll write that is that we have each little piece of flux. I'll give it an index I. So the ith piece of flux is going to be approximate, or is going to be equal to the ith little piece of electric field dot product with the ith surface vector. So that should be it. I should give it delta A because it's a very small surface that's been broken up. All right, so then to get the total flux, we would add those all together. So the sum over all of those I little pieces of the electric field dotted with delta A. So, and you know, just as a diagram here, if I had some kind of a weird shaped surface, you know, what I'm looking at here is each little piece of this, right? This little piece of this surface has a normal to it, and that would be the dA vector. And there's going to be some electric field in space at this point, you know, pointing in some direction. We don't know what direction, right? But you'll have a electric field in some direction there. All right, so we would be looking at each little piece of this surface. We would find the normal for it, the dA. We would find the electric field passing through that surface, and we would find then we would know the flux through that piece. And if we do that for every little piece in the object, then we would have the total flux. Of course, we get to an integral when we take the limit of very small, when we make these pieces infinitesimally small. So in the limit, as delta A is very small, this will be our last equation for today. The general formula for the electric flux is an integral over the surface. And we'll get into actually doing surface integrals. There's very limited to what you have to do as far as surface integrals on the AP test in this class, but you should know they exist. So we're basically adding up all these little pieces dA infinitesimally small over the surface of the electric field dot dA. And this gives us the flux of any field through any surface.
Mr.
Yeah.
Mr. Marco, with the dis so say you have a charge going down your table,
Mhm.
right? And then you take a bit of paper, and it's like, but then the paper won't be straight, it would be a bit curved, right?
Okay.
So the bit that is closer to the table is further away, than the bit that is, you know,
Mhm.
up in the air.
Okay.
So with distance, would that matter?
If that's your, so if the, yeah, so right. I think I see what you're saying. So you're talking about an electric field that's not uniform, right?
Uh,
Because the farther away you get from your charge, the more spread out those electric field lines are going to be.
but yeah, but then a portion of that square is closer to the field than the other part of the square.
Yeah. I mean, so when you're taking the integral, the portion of the square that's closer to the field is going to have more electric field lines pass through it. So we'll have a bigger flux, right? And the part that's farther away from a point charge is going to have fewer electric field lines through it. So that part will have less flux.
Okay.
Does that make sense? I'm not sure if that answers what you're asking.
It does. But then earlier when we were like earlier in the in your explanation, in your lecture, you said you multiply the electric field times the cosine of the area. No, times cosine of theta times the area.
Yeah. Right. So this is
But then, yeah.
for this. So until we get to the integral, we're still doing very special situation where the field is uniform here, and the
Oh, okay, right, okay.
right. So you're right. If we're talking about a point charge, we don't have a uniform field,
Right, okay.
right? And we're getting to the point where we're going to learn how to make a uniform field pretty soon, and Gauss's law will show us where these uniform fields that we keep talking about come from.
Okay.
But yeah, you're right. If we're just talking about a point charge, then you're going to have a different amount of flux through this side of the rectangle than you were through this side of the rectangle,
Yeah.
and that's why you would end up having to do the integral.
That's good, okay.
Good question. Any other questions or comments on the electric flux stuff? We're going to be doing examples with this, so you'll get a chance to work with this and get more comfortable with it, hopefully.